see how y'all did this. There's a couple of ways you can use your calculator to evaluate functions. If you have the function of 1/2 to the x, of course we look at that right there, and we know that that's what type of function? Exponential. Excellent. How do you know? Exponent is what? X, the variable, and the base is what? It's a number, right? It's a number. Now, it's a number in this case that is greater than 0 but less than 1. So that is going to, for larger and larger values of x, going to make that value what? Bigger or smaller? Smaller. So that would be exponential growth or decay? Should be decay. If the function's decreasing, should be exponential decay. Yeah. Absolutely. It's been about 10 minutes. Yeah, thanks for waiting. Yeah, you were. Okay, good. So if you wanted to do f of 0, you could do that one without any calculator's help, right? Let's do that. F of 0 is going to be 1/2 to the 0 power, and what would that be? 1, okay? That's going to be the, what did we call that? If it lands on the y-axis, it is the y-intercept, right? It's the y-intercept. We also said for applications, it's going to be the initial value. Remember, one of the characteristics of exponential growth or decay is that it can't start with 0. All right, you can verify that on your calculator by going either 0.5 caret to the 0 power. 0.5 is another version of 1/2, and it makes it a little bit easier to type in. If you just did 1 divided by 2 to the 0 power, you still get 1. But what is your calculator doing the quantity 1/2 to the 0 power if you type it in like that? If you type it in as 1 divided by 2 to the 0 power, your calculator does exponentiation first. So it's doing 1 times 1 divided by 2 to the 0 power. And 2 to the 0 power is 1. So it's doing 1 divided by 1. You're getting the same answer, but not for the right way. So if you're not going to use the horizontal division bar, you would need to put parentheses around it. Parentheses 1 divided by 2. Now you've got the quantity to the 0 power, and you get 1. Or you could hit alpha trace. Alpha trace gets you to this menu here. Your F1 green menu is unlocked. N over D is numerator over denominator. So maybe you're used to using this. Maybe you're not used to using this. But if you do that, you can click to the right and then say that is all to the 0 power, and you get 1. Okay. Now, the best, most efficient way to compute things is not by typing in your function over and over again. So here's how I want you to get in the habit of evaluating functions. Go to y equals and type it in right there in y1. Now, I would also recommend parentheses. Just better to have them and not need them than to need them and not have them. Type in your 1/2 with your horizontal division bar, close parentheses, and then say it's to the x power. And notice it got rid of the parentheses when I typed it in, because when in math print, when you're actually up elevated as an exponent, it's better than a non-math print. Okay, so there it is in y1. Where do we put our function? In y1. Okay, keep that in your head. Now we'll go to the home screen. Second mode, quits, flush the home screen, clear it. And now we can evaluate what's in y1 by doing the following. If you hit alpha trace, alpha is the green button, and then trace, of course, is F4. Whenever you hit this green alpha button, it unlocks F1, F2, F3, and F4, and you can kind of see the menus there. This is your shortcut to your y's. If you just select 1, there it is. Now, if you open the parenthesis right above the 8, type in your 1/2, 1 divided by 2, close parenthesis, it treats that like f of 1/2. So it'll evaluate at 1/2 the function that's in y1. You hit enter, and you get, oops, I typed it in wrong. We're not trying to do it at 1/2. We're trying to do it at pi. That would be the answer at 1/2. Let's go ahead and do pi. So we'll do f of pi. And so now you can do it again. Alpha trace number 1, open parentheses. Whenever you're using pi, go ahead and use the pi button. It's above the division bar on the second feature. And we get 0. Now, how many decimals do we need to report? We've talked about it this year. 3. And you can either round or truncate. Round or truncate. So there's f of pi. f of 99, now since you have it typed in, all you have to do is hit second enter. Second enter recalls the previous line, or you could just go up there and grab it with your directional pad and hit enter. And then all you have to do is scroll back and change pi to 99. And then you're going to get this wonderful number. You'll see that little capital E at the back end? What does that mean? Good. In your science class, you know that means it's scientific notation base 10. So that's the same as 1.577 if you truncate, 1.578 if you round, times 10 to the negative 30th power. So the E means exponentiated base 10. Right, yeah, well, we're still only responsible for 3. Yeah, the front part is called the Mantissa, and then you have your base times 10 to the negative 30. I just thought that might have affected the times 10 to the negative 30, but it doesn't. No, it doesn't. Now, is that a very big or a very small number? That's very small. It's a decimal with 29 zeros and then a 1. That is very, very, very small, okay? It's so small that it's approaching, well, let me use an arrow. It's approaching what number? 0. So notice I'm going to the right, f of pi, that's f of 3.14. I already get a pretty small number. If I go up to 99, it's like really, really small, approaching 0. And then if you plug in a 999, and again, the way you could do that is hit second enter, or you can go up there, grab it, hit enter, and then scroll back and just add another 9. Or you could just hit alpha trace 1 again. You get 0. And if you write down 0, is that correct? It's basically 0, good, but is it actually 0? No, your calculator's pretty stupid, and you're the boss of your calculator. So if you write down 0, if you put the equal sign and you put 0, you're going to get points taken off. You need to know that it's actually not 0. So why is it actually not 0? Well, if you hit zoom 6, we actually sketch it, you can actually see what the graph kind of looks like. It's exponential decay. So if you wanted to transfer it to your paper, there's the y-intercept. We already said it was 0, 1, and it's coming down like this, and it's getting closer and closer to 0. So what graphical feature do we have on the x-axis? Not a vertical asymptote. We have a horizontal asymptote. F has a horizontal asymptote at y equals 0. So instead of saying f of 999 equals 0, we won't say that, but how about this? The limit as x goes to infinity of f of x equals what? 0, right? Yeah. The numbers are getting smaller and smaller and smaller. But already by 999, the values are so small that the calculator cannot store them, right? At 99, it was storing them, but it was already to the negative 30th power. That's pretty amazing. 29 zeros after the decimal and then a 1. So if you go out, by another factor of 10, it's calculator overload. So this is breaking the calculator. You're getting the calculator to lie to you, all right? So this is why it's important for you to identify exponential functions and know what the graph looks like or what behavior you would expect, before you even go to the calculator. The calculator is only a tool to help you do heavy lifting, crunch numbers that are not very, very pretty. You should already kind of have an idea of what you're expecting as an output. Okay, let's see. We're jumping down here to example 3, still with the calculator. Kind of the same thing. Let f of x now equal 1/3 to the x. Is that going to be growth or decay? It's going to be decay. Go ahead and use your calculator once again to compute those values, A, B, C, and D. And try to do it the way that I just showed you. All right, I'll do it with you over here. I'll do it nice and quietly, and we can compare answers. 3 decimals, round or truncate. A real quick note on notation. F of 2, if you actually did this one, without a calculator, that's just the quantity 1/3 squared. We learned our rule of exponents in the first week of school. That's 1 squared over 3 squared, which is 1/9. If you type that into your calculator and it shows you 1/9, like this, mine did, then you're on automatic probably. So if you go to mode, which is right next to the second key, and you go to the next screen will kind of give you some options. You're in math print, but you can always go back to classic mode, stay in math print. And then here in your answers, you have it on automatic. If you want it to always give you a decimal answer, you can just select decimal right there and then go back to the home screen. And then if you just redo the calculation, it's going to give you this number here, 0.111. All right, so let's talk about preferred answer types. First of all, whenever you're reporting a decimal, 3 again, right? Round or truncate. I like to put the 0 in front of the decimal. I think Mr. Johnson mentioned that he likes to do the same thing. Although it's not required, it kind of helps that decimal stand out. In this case, it's 111. Which answer then is more accurate? The one on the left or the one on the right? The one on the left, right? The one on the left is more accurate because 1/9 is encapsulating the whole number. If you put 0.111, you have now chopped off some of the accuracy, okay? We don't use horizontal bars. You might have learned like in little school that you put like a horizontal bar over it like that, and that means what? Repeating. We don't do that in here. We just report 3 decimals. So 0.111 is not as accurate as 1/9. Now, because it's not exact, is it okay to put an equal sign here, or should we put a squiggle? Yeah, technically a squiggle would be perfectly fine, okay? But if you don't put a squiggle here, if you are ever just reporting an answer from the calculator, as long as you report 3 decimals and you round or truncate and it's correct to those 3 decimals, you are not going to lose points if you use an equal sign here. All right? So I've been telling you all year that when you ever equate 2 things, you need to make sure they're truly equal. This is kind of the one exception, okay? That's the one exception. If you want to put a squiggles there, if you're going to report both of them, that's great. It's better to have both of them than just one of them if you can. All right? So f of -3/4, go ahead and do it if you haven't done it already. I'm going to do it both ways now. I'm going to do it by hand and with the calculator. If we do it without the calculator's help, this is what your line would look like, 1/3 to the -3/4. Let's see if we can evaluate that without a calculator. How can I handle the negative first and foremost? From the beginning of school, if we have a ratio to a negative power, what did we say we could do? To the fraction inside? We could flip it and make it to the +3/4. Okay? Now, of course, anything divided by 1 is itself, so that's going to be the same thing as the 4th root of 3 cubed or the 4th root of 3 quantity cubed. Either one of those is fine. The left one you can actually do a little bit more work. 3 is not a perfect 4th root, but 3 cubed is 27. So the 4th root of 27 is a simplified exact answer. There are no factors of 27 that are perfect 4th roots. It's pretty good to always have a simplified exact numeric answer and then accompanied by a 3 decimal approximation. So if we want to evaluate it, alpha trace number 1, that's where we have our function, and we'll type in -3 divided by 4. And that should be approximately 2.279. Or if you want to round, what would it be if you rounded? 2.28? Or would you need the 0 at the end? Yeah, you would need the 0. Unless it's a terminating 0 and it's 0 forever and ever after that, it's part of the accuracy. So again, the number on the left, 4 through to 27, is more accurate. If you want to put squiggles, you can. But again, here, if you put equals, you're not going to lose points. Now, in this one, we can't really get much satisfaction. If we just plugged it in, that's 1/3 to the pi power. So we'll just do it on our calculator, alpha trace, number 1. We're doing it from the home screen. Plug in the pi again like we did in the warm-up. And you get 0.031 or 0.032. 3, 1. Yeah, either one. I like to truncate. And then f of the square root of 2, that's going to be 1/3 to the square root of 2th power. And there's not much more we could do with that except maybe call that 1/3 to the square root of 2th power. Not a very pretty number. But on our calculator, alpha trace, number 1, open parentheses, type in the square root of 2, click to the right until you're up from under the radical, hit enter, and you get 0.211. All right, so there you are. So we can use our calculator wisely if we're going to be computing things over and over and over again. Put it in Y1 one time, make sure you have it in there correctly, and then compute things from the home screen. That's how I want y'all to get in the habit of doing that, okay? Any questions on that? Okay, so now what we're going to do is we're going to compare some growth and decay functions. We have the first one, we want to sketch 2 to the x and 1/2 to the x on the same set of axes. So let's just do this one. It says to make a table of values, but we'll just make a table of values in our head. The fun part is picking the flavors. Let's let f of x equal 2 to the x be in, I'm going to choose blue. So is that going to be growth or decay? What do you think? Should be growth. Yeah, the base is 2, and 2 is bigger than 1. So let's go ahead and go out to the right. We'll just pick some values. What's 2 to the 0 power? 1. So I'm going to go ahead and put that mark right there. That y-intercept is a very important point. At 1, what's 2 to the first? It's 2, right? So it looks like that. Let's go equally spaced there to 2. What's 2 squared? 4. So notice now the distance from 0 to 2 is going to have to be doubled. I'm up here at 4. And we're already kind of running out of room here. If you plug in a 3, that's 2 to the 3rd, which is 8. That's going to be way up there. So I already can just connect these dots and go like that. And then as I go out to the left, let's plug in a -1. What is 2 to the -1st? Plug in a -1. What's 2 to the -1st? Well, that's the same as 1/2 to the +1st, which is 1/2. Yeah, that's going to be right here at 1/2. If I plug in a -2, what's 2 to the -2nd? Off to the side here. 2 to the -1st is 1/2. 2 to the -2nd is 1/4, right? It's 1/2 squared. So that's now half as tall. Come out here to 3. What's 2 to the -3rd? Well, it's 1/2 to the 3rd, which is 1/8. Yeah, so notice we're getting really, really, really close to the x-axis. I'm already kind of losing my ability to draw it above the x-axis without drawing it on the x-axis. So that's why we just draw it like that. We almost draw it kind of parallel, but getting closer and closer to the x-axis. So not quite parallel. All right, so there it is. There's the function 2 to the x. So let me label it over here. F of x equals 2 to the x. All right, so what would the graph of 1/2 to the x look like? Well, we saw that one in the warm-up. Let's choose, I'm going to choose verdant green for that one. That's g of x. And let's do the same thing. We'll just kind of plot points in our head. What would be g of 0? 1, right? So they share that same point, 0, 1. They both pass to the point 0, 1. Let's do it like we did with 2 to the x. We'll go out to the right first. So if you plug in a 1, what's g of 1? Well, it's 1/2 to the first, which is 1/2. G of 2 is 1/2 quantity squared, which is 1/4. G of 3 is 1/2 quantity cubed. That's 1/8. So if you notice now, this one is going to 0. On the right-hand side, the exact same way f of x, the blue one, went to 0 on the left-hand side. In fact, you could say that all of these values in blue to the left of the y-axis can be obtained by simply doing what across the y-axis? Reflecting across the y-axis, yeah. Should it be any different as we go out to the left? No, not really. If I plug in a -1, what is 1/2 to the -1st? No, it's 2. You're right, it's 2. So that's going to be right here. And what is 1/2 to the negative second? Well, you flip it and square it, and you get 4. Okay, so that's going to be right up here. And what's 1/2 to the negative third? Well, you flip it, flip it and cube it, and you get 8. Yeah, so again, we're kind of running out of room to draw it. We'll do it like this. And this is g of x equals 1/2 to the x. All right, so again, what do you notice about those two functions, 1/2 to the x and 2 to the x? F and g are what? Would you call them mirror images of each other? Yeah. F and G are mirror images, you could say. But you got to define what the mirror is. Mirror images across what line? The y-axis. Good. Across the y-axis. Now, is there a way that we can prove that? Well, the answer is yes. Watch this. Let's start with g of x equals 1/2 to the x. And let's go ahead and simplify that. Let's see if we can write this in terms of base 2. If I want to write that in terms of base 2, I will distribute the x, so that's 1 to the x over 2 to the x. That's legal, right? Just giving each factor the own variable. And what is 1 to the x power? Well, it's the same as 1, isn't it? 1 to the first, 1 to the second, 1 to the third. It's just 1. So that's the same as 1 over 2 to the x. And now if I bring the 2 to the x to the top, we know to do what with the exponent? We make it what? We change the sign, right? So I was able to write then g of x in terms of 2 to the x. So think about transformations. If you take the graph of 2 to the x, which I'll write off to the side here, if you take the graph of 2 to the x and you replace x with negative x, what does a negative do when it's in front of the x, transformation-wise? Reflects it across, not the x-axis, across the y-axis, right? Remember, if it's out in front, that's a reflection across the x-axis, like x squared and negative x squared. But what's happening when you have a negative in front of your x, think of your x's as being horizontal values. When you put a negative in front, you're taking the opposite, and so x values are switching. So if you interchange two x values, you're doing it like this, which is across the y-axis. So a negative in front of the x is a reflection across the y-axis. So there you go. 2 to the negative x is the exact same thing as 1/2 to the x, but you can obtain it from taking your exponential growth function, 2 to the x, and reflecting it across the y-axis. And we just kind of verified that. So let's go ahead and do the same thing for e to the x. Let's pick another flavor. I'll choose beefy brown for e to the x. Now, e is a number with which you are probably not so familiar. It is the second most famous irrational number in all of mathematics, right behind pi. Square root of 2 is also a famous one. Have y'all seen e to the x before? Or just e, the number, not the letter? Hopefully you have. It is 2.718. And it goes on forever like pi. It's a transcendental irrational number. So this one is bigger than pi or less than pi? It's a little less than pi. It's a little less than 3. So you do need to know e to at least 3 decimals. And there's an e button on your calculator as well. Twice. It's twice on your home screen. If you want to know what e is, you could do this. You can hit second ln. It's the second feature on the natural log, because as you're going to learn, natural log is the inverse. And then you can put in a 1, and you get that. Or it's such an important number, instead of doing e to the first, look at what the second feature is on your division bar. You see your division key? The second feature on your division key is just e itself. So e is so important, it appears on your deck of your calculator 2 different times. It's that important. All right? So let's go ahead and see what it's going to look like. We're just going to kind of draw it in here compared to 2 to the x. Do you think First of all, what's the y-intercept of e to the x? What do you get when you plug in a 0? You get 1. Okay, so they again share that y-intercept. Do you think e to the x then is going to be steeper as we go to the right, above or below the graph of 2 to the x? Is it going to be above or below? Above, right? Because 2.7 to the first power is 2.7, not 2. So it's going to be a little bit steeper. So it'll look like this. And we'll just call that f of x equals e to the x. So it goes to infinity a little bit faster. Just like x cubed is steeper than x squared, right? For those power functions, polynomials, the bigger the exponent, the faster it grew. Well, now for exponential growth functions, the bigger the base, the faster it grows. Now what's going to happen on the left-hand side? To the left of 0 is the e to the x graph going to be above or below the blue? It should be below, right? Because the base is bigger when you're raising it to negative powers, it's going to get smaller faster. So you could just say the graph is steeper. E to the x is in general steeper than 2 to the x. And steeper means that it goes to infinity faster and it goes to 0 faster. Now let's pick one more flavor for 1 over e to the x. I'll choose hot pink. Is there a way to now generate the graph of 1 over e to the x just from this beefy brown graph of e to the x? How could I get the graph of 1 over e to the x from the graph of e to the x? Yeah, reflected across what? The y-axis, yeah. So again, we don't have points here plotted, so we're just going to use the good old eyeball method. Looks something like that. And we get y, well, I guess its name is g of x equals quantity 1 over e to the x. So why are we doing this? Well, I want you to understand, like polynomials, the relation among different exponential growth functions based on their base and exponential decay functions. So what can we say? For exponential growth functions, the bigger the base, the whatter the graph? Steeper. Yeah? Steeper. Let's go ahead and write that out over here. So for growth functions, and of course these are exponentials, that's going to be when our base is what? Bigger than 1, less than 1, bigger than 1? Okay. When the base is bigger than 1, comma, we could say the bigger the base, comma, the steeper the graph. In both directions, left and right of the y-intercept. The steeper the graph. It'll go to infinity faster and it'll go to 0 faster. Is that true for decay functions? The bigger the base, the steeper the graph. Well, which base is bigger, 1/2 or 1 over e? Which one's bigger? 1 over e is bigger? Think of e as around 3, right? What's bigger, 1/2 or 1/3? 1/2 is bigger, right? So now you could say for exponential decay functions, you could either say the bigger the base, the what of the graph? Less steep? Or how about this? The smaller the base, the what of the graph? Steeper. There you go. That's a better way to say it. So for decay functions, and of course that's between 0 and 1 for the base, the smaller the base, comma, the steeper the graph. But notice they all pass through the same y-intercept. So that's what you need to get out of this little activity. For growth functions, it's pretty intuitive. The bigger the base, the steeper the graph. But for decay, just think decay is opposite, right? They're getting smaller instead of bigger. The opposite of big is small. You learned that in a Sesame Street book or something when you were young. Well, it's the opposite then in terms of the base. Now, the smaller the base, the steeper the graph. All right, so if you come down here, here is a pretty picture that has different flavors. So functions that are increasing are growth functions. So notice the steepest base that's drawn is 10 to the x. Just underneath that, a smaller base of 5. Just under that, a smaller base of 3. Just under that, a smaller base of 2, right? So as long as the base is bigger than 1, you can kind of fit it in here compared to the others. And the only time we're going to be really showing the steepness of an exponential function is relative to any other thing it's graphed on the same coordinate system with. And then if you come over here to the left, notice what's the biggest base on the left? 1/2, right? And then it starts getting smaller, 1/3, 1/5, 1/10. 1/10. Let's go ahead and draw our new parent function, e to the x, on here. I'm going to go back to Beefy Brown. Where would the graph of y equals e to the x fit in on this graph? Where would e to the x fit in? Between 2 and 3, right? Good. So notice they all share the same y-intercept. So let's draw it in there. It would be right around there. Y equals e to the x. And then on the other side, oof, okay, it's between the pink and the black. It's going to be right in here. There we go. And again, that works because e is approximately what? 2.718. So you can write that as about 2.718 ... to the x power, approximately. It's less than pi. All right, you got it? So let's learn now officially our new parent function. Parent functions, as we encounter them throughout the year, you're responsible for memorizing what they look like and all the characteristics that we've studied in Chapter 2 pertaining to them. So here we are, e to the x. Graph the parent function, then we'll find the domain range, symmetry, blah, 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 blah. So we're going to need ourselves some y-axes and x-axes. There's a good y-axis. And there's a good x-axis. I'll use blue here. So the first point that I'm going to put is 0, 1. That's the y-intercept. And we said e to the x was what? Growth or decay? It's growth. So it's going to look like that. And then you just kind of continue it over here to the left. Now notice, if I did not tell you what function that was, how would you know if that was 2 to the x or e to the x or 10 to the x? Would you know? Well, they all have the same y-intercept, right? We saw that up here. All of those have the same y-intercept. You wouldn't know, is the point I'm trying to make. You wouldn't know without any other information if that were e to the x, 2 to the x, 10 to the x, whatever. We don't really show the steepness of the graph. The only time we show it is relative to another function that's on the same coordinate system. So they all kind of look the same. This could be a representative exponential growth function for any base. You would have to have more information to know it was actually e to the x, such as labeling it, right? Now how do you know that's the graph of e to the x? Yeah, it's labeled y equals or f of x equals e to the x. So let's go ahead and write, let's call it f. It's a parent function. We'll call it f of x. You could also call it the mother function, right? You just got to be careful how you say mother function. So the domain of f is what? All real numbers. Very good. There's not a number in the whole wide world you can't raise to the power and get an output, right? All real numbers. The graph goes everywhere from left to right. What would the range of f be? 0 to infinity. Inclusive or non-inclusive with 0? Non-inclusive, right? We saw in the beginning in our warm-up that the calculator thought that it does reach 0. But our calculator is dumb, stupid, right? We're the boss. So you could either say the set of all y's such that y is strictly greater than 0. Or if you like interval notation, it would be 0 with the parenthesis to infinity. Either one of those. All right, intercepts. We have a y-intercept at the point 0, 1. Do we have any x-intercepts? No, it never equals 0, right? So we'll just put x-intercepts, colon, we'll put none. It gets really, really, really close to 0. Remember, that's what an x-intercept is when the function equals 0. It gets really, really close to 0, but it doesn't actually reach 0. Intervals of increasing or decreasing. Remember, we read a graph from left to right. Is this function increasing or decreasing or a little bit of both? It's increasing. And it's only increasing, right? So what do we call such a function on an interval if it's only increasing? There's two different words. We used it on the last test. We had it in the vocabulary. Monotonic, or, remember I said your parents could be really strict. One rule and one rule only, and it's my rule. So you could say it's monotonic or strictly, either one, increasing. And then we'll say over its domain, which of course we know means for all real numbers. So it's monotonic increasing or strictly increasing. What else does it ask us? Does it have any local extrema? Does it have any local max or local mins? Any hills or valleys? No. So there's no local extrema. Remember, extremal is plural for extreme y values. Does it have any absolute extrema? Is there an absolute maximum value? No, because the y values go to infinity as we go out to the right. Does it have an absolute minimum value? No. So there's no extrema. And of course, if I don't tell you what type, you're assuming that it means what type? Global or absolute. Yeah. It gets really, really, really close to zero, but it never reaches zero. So there is no absolute minimum value. It's bounded by zero, but it doesn't actually hit a lowest number. It would have to be the first real number greater than zero. And there is no such first number greater than zero. What else did we talk about in chapter 2? Does it have any symmetry, even, odd, or neither? No symmetry. No symmetry. It doesn't have y-axis or origin symmetry. Let's do the end behavior. Let's write it up here. What would be the limit as x goes to infinity of e to the x? Yeah, infinity. Or d and e, as some of y'all put on the test. Remember, infinity is the preferred answer because it tells you why it doesn't exist. It doesn't exist because the y values increase without bound. What would be the limit as x goes to negative infinity of e to the x? Well, you can either look at the graph, hop on the graph and go out to the left. What are your y values getting closer and closer to? 0. Or you could actually just plug it in. The cool thing with infinity is you can plug it in. That becomes e to the negative infinity, which is the same as 1 over e to the positive infinity. And what is that approach? If the top stays a 1 and the bottom gets bigger and bigger and bigger, it goes to 0. So that's the left end behavior. So, because the bottom one is an end behavior limit and it equals a finite y value, we could say that f of x has a what? A horizontal asymptote. Good. At y equals 0. But remember, it only affects the graph on which end, left or right? The left. So exponential functions are really, really interesting because they do have a horizontal asymptote, but it only affects the graph on one end. The other end is infinite, and then the other end approaches a finite y value. Okay, there you go. There's your new parent function, e to the x. And again, without looking, e is approximately what? 2.718 ... Yeah, very good. Very good. E to the x, remember, is found 2 places on your calculator. Let's do it again real quickly. It's second ln. Second ln does e to the exponent, so you could type in a 1. Or you hit second division bar if you just want e the number. It is so important, it's on your calculator deck twice, 2 different places. So even though it's the second most popular irrational number, guess which one is actually more important? Yeah, unless you're in geometry, e is actually more important. Or maybe more useful, not to diss pi. This is called the natural base. The natural base. E is called the natural base. It shows up in nature quite a bit. If you've ever seen the spiral, the Fibonacci spiral, yeah, if you look at the Fibonacci series, which is described how like rabbits reproduce, it goes 1, 1, 2, 3, 5, what would be the next number? Do y'all see the sequence? 8, and what would be the next number? 13, and the next number? 21, comma, dot, dot, dot. How are we getting the next number? You're adding the previous 2. So you start with 2 seeding values, 1 and 1. 1 rabbit and 1 rabbit. Okay, and you add them to get 2, add the 2 previous to get 3. So this is how rabbits supposedly reproduce. And it slightly grows faster than exponential. This is called the Fibonacci Sequence. Fibonacci Sequence. Named after Leonardo da Fibonacci, who was from the same hometown as Galileo, which was what? The leading tower city. Pisa, yeah. So sometimes he's called Leonardo da Pisa or Leonardo Fibonacci da Pisa. If you work down and you start taking the limit, if you start taking the limit of right to left, let's take this, 2 over 1, and then 3 over 2, and then 5 over 3, and then 8 over 5, and then 13 over 8. If you keep taking this ratio as you go down the line, guess what it's approaching? Actually, this one might be approaching. You could try that at home. No, it's not approaching 0. You should try this at home. It's kind of interesting. See what number you approach. This was named after Leonard Euler. He's not on my wall. Leonard Euler, it's spelled like this. You might have seen his name and pronounced it Euler. It's Leonard Euler. He's the guy that first did a lot of work with this number and discovered it, which is why we use the letter E to describe it. It's the lowercase of his name. So I guess when you discover a number and its importance, you can name the number after yourself, right? So Leonard Euler discovered the number. We will pick up there tomorrow and make sure you know your parent functions, okay? We're going to do transformations tomorrow. Enjoy the rest of your